Socratic Math Tutor here. So today we're going to find the volume V of the solid of revolution formed when the graph of this equation is rotated about the x-axis over this interval. So let's go ahead and call this something. Call this y of x. And so what we're trying to find is basically the volume of the solid of revolution between x equals 0 and root 3 of y of x. And hopefully, you've probably been doing these all year, so hopefully you know that this is the integral from 0 to root 3 of pi r squared dx. Now, because 90% of the people coming into this probably already know this formula and already understand where it comes from, I'm not going to spend any time explaining it. But if you need an explanation, go ahead and just Google for this phrase in yellow that I've just written, and you should be able to find an explanation. Okay, for the next step, I want you guys to keep in mind the following. Firstly, if I take a square root and I square it, I'm always going to get back x. That makes sense for any x greater than or equal to 0. And there's another version of this, which is taking the square root of a square. And this actually holds for all x in the real line, so it holds more generally. But in this case, we get an absolute value sign popping up. Okay, so have a look here. We've got y of x being squared, and that means that we're doing the square root of something squared. And so which of these two lines is applicable? Just ask yourself that question. You should be able to see that it's this line that's applicable. And so what that basically means is we don't need an absolute value sign in the simplified expression. So with that in mind, let's go up here. We'll get our terminals going. I'll put the pi out the front. We've got this 2 here that's going to get squared once it goes inside here. And so I'll put a 4 here to accommodate that. And then we've got to do the square of this square root, which according to what we said down here is just all the stuff that was in the square root, right? Now in the original problem, the volume we're trying to find is actually called capital V. So let's write capital V equals. And just note here that we're supposed to give our answer in the form V equals 2 pi times some stuff, okay? And so to take that into account, to kind of give ourselves the best chance of giving an answer in the form they want, what I suggest we do here is we rewrite our equation in terms of V over 2 pi, which of course will be 2 times this integral. And that way, once we find this expression, well, that's going to become this stuff in the brackets here. And the 2 pi out the front really just comes from this 2 pi on the left. Okay, so I've gotten rid of most of what was written. That's because we really don't need it anymore. I'm also going to make that a bit smaller and just kind of cram it into the top right-hand corner, just like that. So that'll be a helpful little reference for us. And I also want to make sure that we have a name for this part, because basically to proceed, we'll have to do some partial fractions on this expression. So let's go ahead and call this q of x. I chose q because basically it's a quotient of 2 polynomials. So I've gone ahead and rewritten that just to make it look a little bit nicer. And I'm going to assume that you guys are familiar with partial fractions, so I'm going to go through the next bit fairly quickly. If you're not, at some point I'm going to create a kind of ultimate guide to partial fractions, and when that's ready, it's going to be linked in the description. Okay, so let's go ahead and do partial fractions with q of x pretty quickly. So I'm going to write q of x on the left-hand side. On the right-hand side, I put the general form of its partial fraction decomposition. Implicitly, we're asserting that this equation holds for all x in the real line, except for those x's that make one of these denominators equal to 0, because that will cause the fraction to not exist, because we're not allowed to divide by 0. So in particular, x equals -1 is not allowed, and that's quite simply because x equals -1 causes this to equal 0, which makes this fraction not exist. Okay, so for all x in the real line except for -1, this equation holds. For the next step, we'll multiply through by this big denominator. So on the left-hand side, we're going to get just the numerator by itself. On the right-hand side, the denominators also vanish, and we also get some extra coefficients. So the extra coefficient of a, for example, is x squared plus 1. The extra coefficient of bx plus c ends up being x plus 1. And for this line, we can assert that it's true for all x in the real line. Okay, so we don't need to delete -1. We can actually assert that it's true for all x. And the reason for that is basically that from this line up here, we can deduce that this line is true for all x except x equals -1. And it turns out that if two polynomials are equal for infinitely many points, well, then they have to be the same polynomial. And so therefore, we can assert that this line is true for all x in the real line. Now, there's a nice trick at this point. What we're going to do is we're going to let x equal -1. And that's just to knock this out, and that's going to help us find what a is. So let x equal -1. We're allowed to do that because the previous line is true for all x in the real line, and so it's certainly true for -1. And so what that tells us is that, okay, let's put x equals -1 in. So -1 squared plus -1 plus 1 has to equal a times x equals -1 here, -1 squared like that, plus, and this whole bit at the end can just be left out because x equals -1 will get us a 0 here. So I actually don't need anything else apart from that. And then we just simplify. So here we have 1 plus -1 plus 1. That's just 1. Here we've got a times 2. And so that tells us that a equals 1/2. And so that's kind of a nice way of getting our first coefficient. Okay, so let's get rid of all of that work. What we learned is that a equals 1/2. And so I'm just going to put that straight in, put 1/2 in there. Now, obviously on your working, you're not going to be erasing things like this. But in order to save space, I've just decided to cut out some of the lines. And so now what we do is we expand both sides out. Turns out there's no work to do on the left-hand side because everything is already expanded out. On the right-hand side, we're going to collect like terms. So let's have a look at the coefficient of x squared first. So firstly, we're going to have this 1/2. And secondly, this bx times x is going to give us, another coefficient for x squared, namely b. And so therefore, 1/2 plus b is our coefficient of x squared. Now let's have a look at x. Okay, so there's no x to the 1 terms being contributed by this part. Over here, we get an x to the 1 term through this product, and we also get an x to the 1 term through that product. Okay, and so therefore we need a b in here, and we also need a c, and that'll be our x term. Okay, so for our constant term, we get a contribution from here through this product. And we also get a contribution from here through that product. And so what we put here is we do plus 1/2 plus c. Okay, for the sake of neatness, I just feel like making this a little bigger. So we'll put 1/2 plus b there, just a little bit bigger. And now what we can do is we can equate coefficients, okay? And so the reason that works basically is that because this line is true for all x in R, therefore it's true for infinitely many different x, and therefore these polynomials have to be the same. And what that means in particular is that the coefficients of each term have to be exactly the same. So if we want, we can get a heading going that says Equating Coefficients. We can focus in on our x squared terms. The coefficient of x squared on the left is 1, so I can write 1 on the left. The coefficient of x squared on the right is 1/2 plus b, and so we can put 1/2 plus b on the right. And similarly, we can do the same with our constant term, right? So the coefficient of our x to the 0 term here is 1. The coefficient of our x to the 0 term here is 1/2 plus c. And so this gets us b and c. So b is 1/2, c is 1/2. And remember also from earlier, we worked out that a was 1/2. So all these three numbers we were trying to find they're actually the same number. And at this point, I actually want to put these numbers straight into the place where they belong. So let's get rid of all these. Let's put those numbers straight in there. And keep in mind, this expression here, this was just q of x, right? So we've broken down q of x as a partial fraction. Over here in the integral we're trying to solve, remember our whole reason for doing this partial fraction stuff was to solve this integral. And over here, we've actually got 2 times q of x appearing essentially in our integral. And so just notice that if I put a 2 here, then I can change all these halves to just 1. And so that kind of cleans up our partial fraction decomposition a little bit. 2 times q of x is just this guy. So therefore we learn that v over 2 pi equals the integral between 0 and root 3 of 1 over x plus 1 plus x plus 1 over x squared plus 1. We'll get rid of everything else because the whole partial fractions thing was really just to help us get this line. And for the sake of clarity, I feel like putting some brackets in there. It just looks a little bit nicer. Let's go ahead and break this up into 3 integrals. So we've got the integral from 0 to root 3 of 1 over x plus 1. We've got the integral from 0 to root 3 of x over x squared plus 1. And we've got the integral from 0 to root 3, 1 over x squared plus 1. Let's give these some names. So I'll call this alpha, call this beta, and call this gamma. So that means that v equals 2 pi times some stuff, namely alpha plus beta plus gamma, which was of course exactly what we were looking for. So this bit in here is going to be our alpha plus beta plus gamma. Let's go ahead and find them. Alpha is pretty easy. So the antiderivative of 1 over x plus 1 is log to the base e of x plus 1 from 0 through to root 3. If I put x equals 0 in, I'm going to get log to the base e of 1, which is just 0. And so I don't need to include a term for x equals 0. So this is log to the base e root 3 plus 1. Okay, let's jump to gamma. Gamma is another really easy one. So the antiderivative of 1 over x squared plus 1 is arctan. So arctan of x from 0 to root 3. Once again, the x equals 0 case just vanishes, so we're just left with arctan of root 3. And hopefully you know that this is pi over 3. And the reason is basically that if we write our special angles like this, well, the value of tan goes 0, 1 over root 3, 1, root 3, and infinity. And so because we're in this case, hence the angle has to be 60 degrees, which is just pi over 3. Okay, so finally let's work out beta. Now if you have a look over here, you'll see that we've nearly got the derivative of x squared plus 1 in the numerator, right? The derivative is 2x. We've actually got x here, not 2x. So what I'm going to do is I'm going to put a half out the front. I'm gonna rewrite it so we do have 2x in the numerator. And so this is a half times the antiderivative of all this stuff, which is of course log of 1 plus x squared. Okay, if you can't see why that's the case, go ahead and let u equal 1 plus x squared. But I'm not going to do that because it's too much work and it's not worth it. Get our terminals going. Now, as with before, the x equals 0 case here just vanishes. So let's focus in on x equals root 3. We put it in here, the root 3 gets squared, so we get 3 here. So 1 plus 3 is in the brackets, and therefore 4 needs to go in the brackets. And let's not forget this half out here. And we might as well take this in as an exponent. And 4 to the power of a half is just the square root of 4, which is 2. So beta is log to the base e of 2. So now we just have to put these numbers in and we get our answer. So v equals 2 pi times, now alpha is log to the base e of this stuff, plus beta, which is log to the base e of 2, plus gamma, which is pi on 3. And if you look at the form they want log to the base e of a. So we need to combine the two logs together, which isn't too hard. So the sum of two logs is just the log of the products. And so using that, we can put a 2 out here. Okay, we'll keep the pi over 3 at the end. And there's our answer. And so that's how you find the volume V of the solid of revolution formed by this graph between these two endpoints.